Group 19 Biology Heating Unit, class of 2020 senior design. Our semester was cut short due to coronavirus, so we could not give this presentation in class, so we'll be doing the best we can to be giving it to you online. A little introduction to our group. I am Maxwell Farney, I'm the team leader. Josh Rubis is our secondary leader and manufacturer. Josh Ritchie is our manufacturer and communicator. Tyler Daniels is our designer. Alex Schuster is our manufacturer and communicator, and Josh Kay is our customer communicator. So a little bit about our customer. Our customer is Dr. Andrew Mahone. He is a professor of molecular ecology at Central Michigan, and he is the head of the CMU AME group. Their department just received a grant from the U.S. Science Foundation to further research in Antarctica. They have been on 2 trips before. This grant will allow them to go on a third, and they will be trying to further their research and find any new findings or any changes in their research. So Andy comes to us with his problem statement. His problem statement is global climate change causing genomic changes in aquatic organisms in the Southern Ocean. Basically means, is global warming affecting organisms? How are they adapting? How are they living? Or are they changing at all? What are these changes in water temperature doing to organisms on their day-to-day life? So he comes, he says, can you provide me with a heating element that will allow me to control the temperature accurately underneath the ocean to test this? So now our goal is giving him a project that he can use to further his research in Antarctica.
For our project, we were given the task of creating an underwater biology heating unit. This unit will be used by Dr. Mahone to observe the local aquatic life that lives on the bottom of the seafloor over a 6-month period at an elevated temp to study the effects of global warming on this aquatic life. This unit will be placed up to 100 feet underwater and be taken down by divers through a 1 meter across dive hole and be anchored to the seafloor with a tethering unit that we will choose later on. The heating pad will be monitored by cameras and be brought to the surface for inspection every 6 months. These cameras will be able to live feed to Dr. Mahone on his ship so that they can monitor and see if anything happens or if something were to possibly move this. But luckily, there is not much aquatic marine life down there that's big enough to be able to move this. So we shouldn't have a problem with that.
During our first meeting with our customer, we talked over a list of needs for the design of the project. The big parts were the adequate design durability and corrosion resistance because it will be underwater in Antarctica for an extended period of time. It has to be waterproof underwater and has to be able to manipulate temperature remotely via a sensor, remote, or something that they can actively access. Consistent heating across the face of the plate so that way one area isn't a higher degree and one area isn't a lower degree. And it has to be made of environmentally safe material so it will not damage the wildlife down there. And it has to be easily manufactured in case they plan to make additional models of the heating plate. The experiment of having an underwater heating element is very new and it's only been done 2 times, once in 2017 and once in 2019 by a British team. The 2017 project was done with a heated trace wire through a PVC plastic block, doing a kind of snake formation. And how they did it was they had a control block and a heated block. These blocks were compared, seeing which grew what. And the 2019 study was done almost the exact same way, just with a few different tweaks and measuring methods.
Our team has researched industry standards which affect the design and intended function of the biology heating unit. The interrupting rating, defined by OSHA, states how equipment must be designed with overvoltage protection to interrupt circuit voltage at specified fault levels to avoid injury or damage. A standard set by the American Academy of Underwater Sciences states how underwater equipment supplied with power from the surface must be disconnected from that power source before being placed into or retrieved from the water and cannot be supplied with power until instructed by the diver. Moving on to our concept fundamentals, our team has selected a voltage controller to be used as a supply power source. In order to follow our standards, the selected voltage controller is equipped with overvoltage protection and will be able to be disconnected from the heating element, which will be inside the biology heating unit and then reconnected when desired. This voltage controller will be interacted with from above the water and in a sheltered field station. The biology heating unit itself will be placed underwater, which required our team to search for corrosion-resistant material to use, such as stainless steel, as an external surface.
All right, our 3 design concepts were a sandwich panel with a heating pad, a heating wire embedded in epoxy, and a heating pad embedded in epoxy. Our first idea was a sandwich panel in a heating pad. So we would take a heating pad and we would take 2 plates of aluminum or stainless steel, and we would use the CNC machine to carve out a place for the pad to go into, and then we would bolt the 2 pads together to create a watertight seal between the 2. Our next one was a heating wire embedded in epoxy with a plate in it. So we would take the CNC machine again and carve out a hole in a piece of aluminum or stainless steel, and then we would take our heating wire and we would run it back and forth, and then we would use epoxy to keep it in there and keep it watertight. Our third and final option was a heating pad embedded in epoxy. So what we would do is we would take stainless steel sheets and we would use the lab to bend up the sides, and then we would weld the sides together, making it a little tub, as you would say. And then we would take our heating pad, put it inside, and then put epoxy in it to make it watertight. And this is the design that we ended up going with. Yeah.
Okay, so we have our concept scoring matrix, and it's basically a matrix to help determine the design process using 3 qualities. So those 3 qualities are the customer needs, the importance of the customer needs, and then the needs that the design fulfills. So from the concept scoring matrix, we are able to score each of our 3 designs and figure out which one will be the best design for our project. Design concept 1 was scored at 191, design concept 2 was scored at 153, and design concept 3 was scored at 203, and the highest number was design concept 3, so that's the one we would design for our project. From there, we were able to determine the cost of our model. So we have epoxy at $80, a heating pad at $226, a power supply at $456, stainless steel at $229, and a power cord at $140, giving us a total of $1,171.
For our final design, we will be taking a stainless steel sheet and be bending the edges up and then welding the corners. On our PowerPoint, you can see on the right where this pink fluid is this what the box will look like, and then we will be sticking the heating pad to this and then covering this pad with a thermally conductive epoxy that a manufacturer has supplied to us. On the left, you can see a potting system. This is what most manufacturers do and what we're actually going to do. What this does is it's going to be able to keep the salt water out and not allow the salt water to corrode and short circuit this pad, because if it does short circuit, there's going to be massive issues and it's going to immediately stop working. Being that this is such a low power unit, if it did short out, it's not going to like electrocute stuff that's on it or do any harm to aquatic life that will be around it. We will still have fuses and other things built into this system so that if something does go wrong, it will not harm anything or catch anything on fire. With this whole current world situation, we're not going to be able to finish this project and deliver it to Dr. Mahone. We would have been able to finish this by March 15th for the early prototype, and then early May, late April for final delivery, where Dr. Mahone will be able to take this and use it for his research purposes. We're going to give our products that we bought to the next semester's class so that they can pick up where we left off and give them a good blueprint idea of what they need to do to finish this. We have all of our things, but we didn't have time to put it together before the coronavirus had broke out. So we're pretty much done with the semester. We're going to be able to finish our report, and that is it.